Okay, here we go. I'm making this diagram. I formed a line down here on the ground. This one would be the sky. We'll just say the sun, even though it's way bigger than what the sun would be. Now each of these angles is 15, or what did I make it? 10 degrees. So here's straight up. Now if my lines aren't perfectly straight, who cares? But we'll say that's straight up, 10 degrees, 10 degrees. Now I do the same thing over here. There's 10 degrees, there's 10 degrees. So what we're going to see is the observers down here. So each parts of this sky contain different, or of the angles contains different amounts of actual sky. Here you got 10 and 10, they're straight up above you. You know, 10 to the side, 10 to this side. And you got the width of a little over 2 of my suns right there. Now farther down over here, I can get about 4.5 in there. Still 20 degrees down here to me. Just like this is 20 degrees. But because in the flat earth model, or at least my version of it, the sky and everything in it is moving parallel to the plane of the earth down here, the ground. Now this, because there's way more distance in that 20 degrees of total space, it's going to take the sun, if it's moving across the sky, much longer to get through that space than it does this little space. Now this is the reason why the EQ mount fails and begins to track inaccurately the sun or anything else as they go towards the horizon. The EQ mount is basically set on a timer, 15 degrees per hour, right? So it's just continuously going. It's not slowing down for anything. It's just going to go in this, like this arc right here at 15 degrees per hour. So because there's actually much further space to go through here, the sun is going to seem to be hanging up. Now the globe earthers, you know, the Wolfies and the Bob the Science guys and NASA shrills and guys like that, will say it's because of refraction. And I believe Wolfie said it could be up to 1.5 degrees. And so they'll actually end up telling you that the sun actually has gone down, but we're seeing it refracted back up. So that's their magical potion to explain why the sun hangs up and the EQ mount keeps on arcing down as if the sun went down when it's still up. Well, it's because of these foreshortened angles. The sky, it's a lot more sky contained in those 20 degrees than the amount of sky in these 20 degrees. That's a foreshortening effect. When the angles become more acute down here, it gets worse and worse. And that's why when they track stars and stuff and planets and all the other things for astrophotography, they prefer to stay more in the middle part of the sky, you know, the high points, because there's less change, and so they can get their pictures. They don't track from horizon to horizon. Now I remember when all these guys, back when I first became a flat earther, they would say, guys like Wolfie, that an EQ mount proves the globe because it can track on a one-axis rotation from horizon to horizon. In fact, they said it can go all the way back around and still be on track. Well, we don't see that, and Wolfie and Bob actually did a video explaining the problems with the EQ mount near the horizons. Of course, and they say that they have a fix for it, and it's called the King's rate. All the King's rate is an adjustment in the rotational speed. So instead of rotating at 15 degrees per hour, it slows down, because that's the only way it can track the sun from one end to the other. It can't do it at 15 degrees per hour because the earth is flat. It's not a globe. The EQ mount was designed for a globe, but it fails at the horizons, just as predicted by a flat Earth, where the sky is moving parallel, like my model right here. Now I'm going to show you one more thing here, why we can get 69 miles per degree angle measurements. Well, that's because the same reason here. Just take this thing. Let's say we're on the flat Earth, the flat sky going across, and I just take, all I do is just take this point and move it. Now all those angles, now the straight up would be here, the 10 and 10, and the same thing over there. They're always going to be covering the same amount of sky. So basically all you have to do is, it's a perspective angle. You just take it from your, we're going to pretend that this is all sea level, by the way, down here. This is all sea level. So as you move, these angles will all cover the same amount of total sky as they do right here. I just moved them further towards the left. But they always cover the same amount. So all you do is just move, take your measurements every mile if you have to, or do it every 5 miles. Take a reading, because now the reading is from the new point. It would be instead of right here, you know, now it's over here, but it's straight up, and those are now pointing over here somewhere. And so you're going to end up always, whatever amount of miles you end up measuring that it takes to drop like Polaris 1 degree, that's how you're going to get it. You're not taking just an initial line up and down, say this is Polaris, and 10, 10, 10, 10, because those are going to become longer and longer in each section, and so it wouldn't work. But when you're actually taking your measurements from your position, it does work, and that's how you'll always end up with the same amount of miles per degree. So anyhow, this solves both problems. All this is predictable. You can see it, and it predicts everything that the globe says can't be predicted by a flat Earth model. They say we can't prove the 69 miles per degree, and that only refraction can make the sun seem to stay up longer than what the EQ mount wants to stay up for. So anyhow, those are two of their arguments shot to